Annyeonghaseyo.
Bang siapa?
Annyeonghaseyo, Pak.
Iya.
Halo, Pak.
Nama
Mbak.
ya. Udah kelihatan itunya layarnya?
Udah, Pak.
Sudah, Pak.
Bagaimana wajahnya? Sudah kelihatan?
Kelihatan, Pak.
Sudah, Pak.
Sinyal, Pak.
Yo. Iya. Baik. Topik pokok bahasan kita minggu ini terkait dengan transformasi Fourier discrete. Ya. Transformasi Fourier discrete, ya. Kita sudah melalui sebelumnya minggu lalu itu deret Fourier discrete, ya. Sudah melalui deret Fourier discrete. Apa perbedaannya? Apa tujuannya? Ya, tujuan dari transformasi maupun deret untuk mendapatkan, ya, analisis di domain frekuensi. Ya, untuk mendapatkan analisis di domain frekuensi. Ketika kita bicara minggu lalu deret, maka mendapatkan domain frekuensi yang kita dapatkan adalah spektrum frekuensi diskrit. Ya. Spektrum frekuensi diskrit yang ditandai dengan koefisien dari koefisien Fourier-nya. Ya. Tandain dengan koefisien Fourier-nya dengan sinyal deretan yang periodik. Ketika kita memiliki deretan periodik, ya, minggu lalu, maka untuk menganalisa di domain frekuensi, spektrum frekuensi, maka tools yang digunakan adalah deret Fourier discrete. Yang kita dapat adalah spektrum discrete K. Ya, jadi discrete to discrete, tapi deretannya periodik. Sebelumnya lagi, ada terminologi transformasi Fourier waktu diskrit, FWD, yaitu deretan terbatas. Jadi transformasi Fourier waktu diskrit deretan terbatas, kita mendapatkan spektrum, ya, continue X, E, pangkat J omega, spektrum continue. Nah, hari ini kita masuk ke discrete Fourier transform, ya. Inputnya adalah deretan terbatas. Kalau deret dari periodik, ini tidak periodik, terbatas. Tetapi output yang diharapkan adalah spektrum discrete, ya. Spektrum discrete. Spektrum discrete yang diharapkan bentuknya spektrum discrete, ya. Bagaimana kita menginterpretasikan, ya, discrete Fourier transform, ya, yang spektrum discrete-nya, hubungan antara transformasi Fourier discrete dengan transformasi Fourier waktu discrete, ya, yang satu continue TFWD, yang satu TFD, yang discrete, ya, spektrumnya dicuplik dengan proses pencuplikan. Kemudian memperkenalkan konsep zero padding. Nah, itulah kira-kira rangkuman dari pokok bahasan kita hari ini, ya. Jadi transformasi Fourier waktu diskrit, domain sinyal waktunya adalah diskrit yang terbatas, ya. Kemudian yang panjang terbatas tapi mendapatkan frekuensi yang spektrum yang diskrit, ya, tools yang digunakan transformasi Fourier discrete. Jadi transformasi Fourier discrete adalah suatu spektrum sebagai suatu deretan, ya, fungsi K integer, deretan. Nah, transformasi Fourier discrete sangat penting di dalam implementasi berbagai algoritma pengolahan sinyal secara digital. Ya. Yang populer untuk komputasinya, algoritmanya adalah fast Fourier transform. Sehingga untuk mendapatkan suatu persamaan transformasi Fourier diskrit atau mendapatkan suatu spektrum yang diskrit, ya, spektrum diskrit, maka kita bisa menggunakan pendekatan deret dengan mengambil deret terbatas seolah-olah periodik dengan periode n, ya. Jadi X periodik adalah suatu penjumlahan dari deretan terbatas yang muncul secara periodik n, ya, dengan periode n. Jadi kalau kita sudah memiliki deretan terbatas seolah-olah dibikin deretan periodik, maka mendapatkan spektrumnya bisa menggunakan tools deret Fourier diskrit. Ya, kurang lebih salah satu cara adalah bagaimana transformasi Fourier diskrit didefinisikan dari mengambil asumsi sinyal periodik adalah sinyal terbatas yang penjumlahannya yang muncul secara periode n, yang disebut dengan sinyal periodik adalah sinyal X, deretan X, n modulo n, yang muncul setiap periode n. Sehingga kita dapat spektrumnya dengan pendekatan deret, kita mendapatkan spektrum frekuensi K periodik, dan spektrum frekuensi yang terbatas satu periode itu adalah definisi dari transformasi Fourier diskrit. Ya. Sebagai catatan, minggu lalu kita telah mendefinisikan koefisien Fourier, ya, koefisien Fourier yang menggambarkan spektrum frekuensi diskrit adalah penjumlahan satu periode 0 menuju n-1 dari deretan periodik dikalikan Wn Kn. Wn pangkat Kn. Ya. Dan deretan periodik Xn, inverse-nya seper-n, penjumlahan, ya, karena domainnya K, jadi K dari 0 sampai N menuju 1, Wn pangkat minus Kn. Ya. Di mana Wn, ya, frekuensi fundamental adalah E pangkat E minus J2pi dibagi N periode. Sehingga untuk satu transformasi Fourier diskrit, ya, mengambil satu periode terdefinisikan, ya, penjumlahan Xn sebagai domain input, deretan input n dari 0 sampai n-1 yang dicari Xk, ya, Wn pangkat Kn, K-nya 0 sampai n-1. 0 untuk nilai lainnya, ya. Dan deretan atau inverse Fourier transformnya, discrete Fourier transformnya seper n, penjumlahan Xk, ya, karena diketahuinya Xk, K0 sampai n menuju K0 sampai n-1 dari Wn minus Kn. N-nya dari 0 menuju n-1, ya. Di mana Wn tadi adalah E pangkat minus J2pi dibagi N periode. Ya, Wn-nya adalah E pangkat minus J2pi dibagi N. Contoh, ketika kita memiliki Xn, ada 5 titik, ya, yang besarannya 1, 1, 1. Kalau diperiodikan dengan periode 5, berarti dia muncul lagi, ya, di berikutnya seterusnya, ya, seolah-olah N5, ya. Kalau dimasukkan ke definisi, ya, tadi definisi 0 sampai N, min 1, 0 sampai 4, E pangkat minus J 2πk dibagi N, periode 5 kali N, ya, penjumlahan geometrik ini kita tahu adalah 1 dikurang E minus J 2πk dibagi 1 kurang E pangkat minus J 2πk per 5. Ini sama dengan 5 untuk K, 0, dan periodanya. Dan 0 lainnya. Jadi kalau kita gambar, di K sama dengan 0 dia 5, ya, sisanya 0 kecuali di periodanya, muncul di periodanya. Ini spektrum fasanya. Jika periodanya di 10, artinya ada penambahan 0. Ya. Penambahan 0 sebanyak 5, karena tadi ada 5 tambah 5. Ya. Sinyal periodiknya muncul. Ya. Sinyal periodiknya muncul setiap periode N10. Ya, periode N10. Kemudian dievaluasi untuk satu periode. Tapi N-nya udah 10. Ya, satu periode N-nya 10. Maka XK-nya ada 10 sampel. Ya, discrete-nya. Ya. Jadi kalau tadi diperhatikan ada titik 0, di antara 0 ini ada nilai-nilai sampel baru. Ya. Dan fasanya juga memiliki fungsi ganjil. Kalau N-nya diperbesar 100, ya berarti di sini ada N-nya 20. Ya, berarti ada lagi di antara ini ada nilai. Ya. N-nya 100, dia semakin rapat.
Hello friends, today we are going to see a problem on DFT using matrix method. So we'll be using matrix method to solve a DFT problem. Now, what is the benefit of using this method? This method is used to solve the problem faster as compared to formula. We will be using formula, but we will be using multiplication using matrix. So that really speeds up the process. This really helps in lengthier problem. So you can solve the lengthier problem easily using this method. So what is this matrix method? Now, let us say that my definition of DFT is x of k, which is equal to summation n is equal to 0 to n minus 1 x of n e raised to minus j omega n, or I should write 2 pi k by n instead of omega. Okay, so instead of omega I will write 2 pi k by n. So that is the definition of my DFT. So I'll write it again. It gives n is equal to 0 to n minus 1 x of n e raised to minus j 2 pi nk by n, where my k is ranging from 0 to n minus 1. Right? Now, suppose let us take for example capital N is equal to 4. So this is also called as 4-point DFT. So in general, any problem in DFT is called as n-point DFT. Now, for a 4-point DFT, if I will express this form, it will look like n going from 0 to n minus 1, which is 3, x of n e raised to minus j 2 pi nk by 4. Right? So if I cancel this 2 with this 4, I am going to get summation n is equal to 0 to 3 x of n e raised to minus j pi n k by 2, because I have divided this 2 with this 4. So I got pi by 2. Now next, let us substitute the values of n. So when I substitute the value of n, I will get x of 0 e raised to 0 plus x of 1 e raised to minus j 2 pi. We have nk, the n value is 1, so I get k by 4. Okay, you can either write pi k by 4 or you can write pi k by 2 if I cancel this by 2. Okay, so either I'll get pi by 2 or 2 pi by 4, no issues, plus x of 2 e raised to minus j 2 pi. Now n value is 2, then k by 4, that is when n is equal to 2, plus x of 3 e raised to minus j 2 pi 3k by 4. So what we have done is, in that formula I have substituted the values of small n and we have elaborated this series. Now if I rewrite it properly, I am going to get x of 0. What is e raised to 0? It is 1, right? Then plus x of 1 e raised to minus j 2 pi k by 4. So I can write it as e raised to minus j pi k by 2 plus x of 2 e raised to minus j, this is 4 by 4, so it becomes pi k, plus x of 3 e raised to minus j, this becomes 6 pi by 4, which is 3 pi by 2. Right. So now this is my x of k. This equation now is a function of k alone. Now I will go on putting the value of k. So when I put k is equal to 0, I'll get x of 0, which is x of 0 into 1 plus x of 1 e raised to this I'll put as 0, so it becomes e raised to 0 plus x of 2 e raised to 0 again plus x of 3 e raised to 0 again. This is because I have put it k is equal to 0. So I will get capital X of 0 equals to small x of 0 plus x of 1 plus x of 2 plus x of 3, because all e's we have as 1. Then I put x of 1, I will get x of 0. Now it will not affect over here because n is 0, so whatever the value of k is, this factor is always going to be 1 plus x of 1 e raised to, now I am going to put k as 1 over here, so I am going to get minus j, okay, 2 will use this, it will give me, okay, let us use this 2 pi into 1 by 4, which is ultimately result into pi by 2 alone, plus x of 2, let me use this, e raised to minus j pi, because here k is equal to 1, plus x of 3 e raised to minus j 3 pi by 2, because here also k is equal to 1. Similar fashion, if I put x of 2, here the value of k is 2, so I write x of 0, first term doesn't matter, it multiplies by 1, then x of 1 e raised to minus j, let us use this, pi by 2 into 2 will give me pi, right, because I'm putting k value as 2, so if k is 2, 2 and 2 will get cancelled and I get e raised to minus j pi, plus x of 2 e raised to minus j let us use this, minus j pi into 2. So that will give me 2 pi. Okay, plus x of 3 e raised to, here if I put 2 now, it becomes 6 pi by 2. Okay, 6 pi by 2 can also be written as 3 pi. Okay, so I'll get minus j 3 pi. Again I repeat, when I put k is equal to 2 over here, 2 into 3 will give me 6, 6 by 2 will give me 3 back, or this 2 and this 2 will get cancelled and I get 3 back. So it is 3 pi. Then lastly we'll put x of 3, which is x of 0 into 1 plus x of 1 e raised to, let us come back here, minus j pi by 2 into 3. So it will give me 3 pi by 2 plus x of 2 e raised to minus j. Now here let us put k is equal to 3. So I'll get 3 pi plus x of 3 e raised to minus j. Now when I put 3 here, it is becoming 9 pi by 2. So it is 9 pi by 2. Okay. So what you see is, as I am going on changing the value of k, so I'm changing the value of k in this fashion, k is equal to 0, 1, 2, 3, I am developing a new row. So this is a complete row. So I am developing a complete new row in which x of 0, x of 0, x of 0 is the first column element, x of 1 is the second column element, x of 2 is the third column element, and x of 3 is the fourth column element, with a multiplying factor of e raised to, let us say, e raised to minus j 2 pi nk. We will have x of written as x of 0, x of 1, x of 2 and x of 3 over here, which I write it as a column, and I have a second column which I write as x of 0, x of 1, x of 2 and x of 3. Right. So this column is having 4 rows and it's having 1 column. Similar way, I have here 4 rows and 1 column. Now I have something to multiply with x of 0, x of n, such that they will produce x of 0. So I have a matrix which is a 4 cross 4 matrix, because the inner dimension of the matrix should match. For that reason, we have to keep a 4 cross 4 matrix. Now this matrix is called as twiddle matrix. So a new term has come in picture which we call as a twiddle matrix. Now let us see what is this twiddle matrix set and how to develop it. So in the definition of DFT, we have x of k, which is equal to summation n going from 0 to n minus 1, x of n e raised to minus j 2 pi nk. Right. So I say twiddle factor as this, we called it as a twiddle factor. Now the twiddle factor definition is given as wn raised to 1 is equal to e raised to minus j 2 pi by n. So here the factor is into 1. So when we write wn raised to 1, it is equal to e raised to minus j 2 pi by n. The index of w is positive, whereas the index of j is negative in exponential term. So if I replace it, it becomes x of k, which is equal to summation n going from 0 to n minus 1, x of n w n raised to, now instead of 1 I have here nk, so I will write nk. So this factor is called as a twiddle factor. Okay, now instead of every time calculating the twiddle factor, let us see a simpler way. we know that we are in an omega domain or a Fourier domain, which is discretized or which is sliced up into some points. Now let's say that in our previous example our n is equal to 4. So I'm going to chop up this circle into 4 equal parts. So my chopping will be 1 point over here, 1 point let's say over here, 1 point let's say over here, and 1 point let's say over here. The value over here is 1, value over here is minus 1. Value at this point is j, value at this point is minus j. Okay, now this factor or this value we called as w4 raised to 0, which is nothing but equals to 1. Then we have this factor as w4 raised to 1. Then this factor is given as w4 raised to 2, and this is w4 raised to 3. So I have 4 components: w4 raised to 0, which is equal to 1, w4 raised to 1, which is equal to minus j, w4 raised to 2 equals to minus 1, and w4 raised to 3 equals to j. Now I will develop that matrix. Now the matrix, every matrix has a number of rows and number of columns, right? So this will be our 4 cross 4 matrix. That means there will be total 16 elements. So the first element is w4 raised to 0, because here the value of k will be 0. If the value of k is equal to 0, the whole row will have the index as 0. So this will be w4 raised to 0, this will also be w4 raised to 0, and this will be w4 raised to 0. Then I will shift to next value, that is the k is equal to 1, and I am going to get a new row. But in that row I have n factor also changing. So when I put the value of n, it will affect in this direction. So for the first column the n value is 0, for the second column n value is 1, for the third column the n value is 2, and the fourth column the n value is 3. So I will get here everywhere the n is 0. I have the factor with wn raised to nk. If k goes 0, then also this product will turn to 0. If n goes 0, then also this product will turn to 0. So now I will have w4 raised to 0, w4 raised to 0, and w4 raised to 0 over here. Okay, then I will have here as w4 raised to, now if k is also 1, n is also 1. So when n and k I put, I get 1. Then I have w4 raised to n is, okay, let us say this as k is equal to 2, this is the row, and k is equal to 3, this is will be the row. So here k is 2 and n is 1, so you get 2. Here k is 3 and n is 1, so you get 3. Now k is 1, n is 2, you get 2, and here it will be 3. Here it will be 2 2s are 4, and here it will be 6 because 2 3s are 6. Here it will be again 6, and here it will be 3 3s are 9. Now you would ask a question that, okay sir, previously we have seen that there are only 4 values, w4 raised to 0, 1, 2 and 3. How to get the values as w4 raised to 4 and w4 raised to 6 and w4 raised to 9? And the logic is very simple. As we are moving on a circle, so this is my circle, and I have 4 points on the circle. I call this as w4 raised to 0, this we call as w4 raised to 1, this we call as w4 raised to 2, and this we call as w4 raised to 3, right? Now when I go from here, I get 0, 1, 2, 3, then we have 4, which is this point again, then 5, this point again, then 6, this point again, then 7, 8, 9, 10, 11, and n number of points I can calculate in this way. Okay, so as I'm moving on circle, after 3 the fourth value is the 0th value again. Okay, so based on this, let us find what is this 4 cross 4 matrix look like. Now w4 raised to 0 is equal to 1, w4 raised to 2 is minus 1, this is minus j, and this is j. So we have w4 raised to 0, so there will be all ones. Here will be also all ones. Then here it is w4 raised to 1, which is minus j. Then w4 raised to 2, which is minus 1. w4 raised to 3, which is j. Then we have w4 raised to 2, which is minus 1. Then we have w4 raised to 4, which is 3, and then 4, which is 1. w4 raised to 6, which is 4, 5, 6, minus 1. Then w4 raised to 3 is j. w4 raised to 6, so this is 4, 5, 6, which is 6. w4 raised to 9, now 6, 7, 8, 9, which is minus j. Okay, so the matrix says 1, 1, first row, first column, all ones, minus j, principal diagonal, j, j, opposite to principal diagonal, minus ones in a rhombic shape, and 1 at the center. So this is a twiddle matrix for a 4-point DFT. Now, just for an example, because I asked that let us solve a problem, so let us take x of n as 1, 2, 3, 4. So if I take an example of 1, 2, 3, 4, then my x of k will be equal to a twiddle matrix into my x of n, which is 1, 2, 3, 4. And now I know, because it's a 4 cross 4 matrix, because my n is given as 4, so my twiddle matrix will be 1, 1, 1, 1, 1, 1, 1, minus j, 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 minus 1, minus 1, minus 1, minus 1, 1. Okay, so here we have developed this matrix, and we have this 4 cross 1 a column matrix. So because the inner dimension matches, of course we can go for the matrix multiplication. Now in this matrix multiplication, we always know that the column will be multiplied by the row. So I have a column multiplied by row. I'll get 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3 plus 4, which is equal to 10. Always remember, the first sample in DFT is always the multiplication of the samples in the x of n. Next, we will have 1 plus, with this as minus 2j. So when I multiply 2 with minus j, it becomes minus 2j. Then I multiply 3 with minus 1, it is minus 3. 4 with j, it becomes plus 4j. So that is going to be, the real terms will be added together and the imaginary terms will be added together. The real terms addition will give me minus 2, and the imaginary term will again give me minus 2. So minus 2 plus 2j, because 4 is positive over here, so it will be plus 2j. Then for the third, I will have 1 minus 2 plus 3 minus 4. So that will give me 3 plus 1, 4, 4 minus 4 is 0, and this will be minus 2. And lastly, we will have 1 plus 2j, which this is plus, then it is minus 3, and then lastly minus 4j. So this will come as minus 2 minus 2j. So the final answer of x of k is 10 minus 2 plus 2j minus 2 minus 2 minus 2j. So if I know this matrix, the calculations are very simple, and it will give you results very faster as compared to solving the whole equation of definition. Thank you.
Hukum konvolusi sirkular. bersifat linear jika X1N pasangannya X1K, X2N pasangannya X2K, ya, dia bersifat linear jika pengali A X1N tambah B X2N, dia menjadi A X1K ditambah B X2K. Ya. Di mana panjang deretan transformasi Fourier discrete adalah harus sama dengan maksimum panjang dari mana lebih panjang X1N atau X2N. Ya. Atau mengambil suatu N yang baru, yang lebih besar dari periode X1, titik sampel X1N dan X2N, dengan menambah 0. Ya. Pergeseran sirkular. Ya. Pergeseran sirkular, jika X1N digeser, ya, maka dia ada faktor WN, ya, faktor pergeserannya. Ya. Nah, sinyal periodik N tadi adalah X, sinyal X, N modulo N. Ya. Dan spektrum periodik K adalah X, K modulo N. Ya. Maka sinyal periodik N adalah X1 N modulo N, maka spektrum X1K-nya, ya, X1K modulo N. Nah, pergeseran, ya, kita lihat pergeseran, spektrum N digeser sejauh M, maka ada faktor pergeseran W N pangkat KM, ya. K-nya dikalikan dengan M. Ya, kalau dilihat di gambar, XN, nah, N-nya 0 sampai 5, kalau module N, ya, dia akan muncul lagi. Nah, kita perhatikan, jika digeser 2, ya, XN adalah satu periode diambil dari yang periodik tadi. Jika digeser 2, XN tambah 2, berarti digeser ke kiri. Ya. Digeser ke kiri, ya, digeser ke kiri. Nah, ini digeser ke kiri, maka yang 2 di kiri ini menjadi ke kanan. Ya. Digeser ke kiri, menjadi ke kanan. Ya. Nah, kita lihat di sini, digeser lagi, seandainya ini digeser lagi, maka kalau dia ke kiri, ini tambah ke kiri 1, yang ujungnya pindah ke kanan. Itu operasi modulo. Ya. Operasi modulo. Jadi, transformasi Fourier discrete, WA6 4K sama dengan WA6 minus 2K. Ya. Balik dia ke sebelah kanan. Secara umum, WN pangkat MK sama dengan WN pangkat minus N kurang M K. Ya. Sifat dualitas. Periodik XN melalui deret dapat spektrum periodik XK. Jika periodik XN dibalik N X sinyal periodik minus K. Ya. Jika dipertukarkan dia, maka bentuknya akan bertukar, sifat dualitas. Ya. Ya. Jika XK Ya. Real xn, ya. Simetris. Real dari deretan periode xn adalah fungsi genap. Bagian imajiner dari deretan periodik xn adalah fungsi ganjil. Maka fungsi genap, ya, pasangannya adalah real dari spektrum xk periodik, dan deretan periodik ganjil adalah imajiner spektrum frekuensi periodik K. Ya. Sifat simetris dari transformasi Fourier diskrit, real dari deretan xn itu bersesuaian dengan spektrum periodik, ya, yang even, dan imajinernya bersesuaian dengan spektrum periodik yang odd, ya. Dan sinyal xn pasangannya bagian real dari xk, ya. Deretan ganjil bersesuaian dengan bagian imajiner dari xk. Ya. Nah, dalam konsep konvolusi dalam deretan terbatas ini, ya, dikenal dengan konvolusi sirkular. Sebelumnya kita mengenal konvolusi linier, ya, konvolusi linier. Nah, konvolusi sirkular, di sini diperkenalkan konvolusi sirkular, ya, konvolusi sirkular. X1n konvolusi sirkular dengan X2n itu adalah didefinisikan sebagai X3n, ya, penjumlahan dari mn-1 dari X1 periodik xm, X2 periodik n kurang m, ya. Jadi periodik itu adalah X1 m modulo n dan X2 n modulo n. Jadi jika X1 panjangnya n, X2 panjangnya n, maka konvolusi sirkular X3 deretannya juga panjangnya n, ya, penjumlahan 0 sampai n-1. Berbeda dengan yang linier, dia akan, jika panjangnya n, yang satu m, ya, dia n tambah m kurang 1, yang bergeser, bertambah. Yang sirkular, dia operasi modulo, dia tetap di sepanjang itu. Ya, notasi dari sirkular, ya, konvolusi linier tidak ada sirkularnya. Nah, konvolusi linier, notasi konvolusi linier dengan ada sirkularnya. Nah, berbeda dengan yang periodik, di dalamnya dikasih n, menunjukkan periode ke n. Tapi dalam operasi sirkular dan periodik, ya sama. Ya. Cuma periodik dipakai di istilah deret, sirkular dipakai di istilah deret, transformasi Fourier diskrit. Ya. Di X3n didefinisikan X1n konvolusi sirkular dengan X3n, X2n sama dengan X3n, ya, adalah penjumlahan dari M 0 sampai N-1, X2M, X1 N dikurang M modulo N, di mana N-nya dihitung, dikomputasi dari 0 menuju N-1. Ya. Nah, di sini variabel barunya M, jadi di N sama dengan 0, dia menjadi ada pencerminan. Ya. Ini X1 contoh, X1N delta N kurang N0, dia hanya ada N, di N0 sama dengan 1, sisanya 0. Di konvolusi sirkular dengan X2 yang panjangnya N, ya. Dia menurun, panjangnya N, di N sama dengan 0. N0 sama dengan 1, ya dia bergeser 1. Nah, yang X2, jika X2 N sama dengan 0, ya. Jika N sama dengan 0, X2 0 kurang M, ya. Ini tetap sama dengan sebelumnya, ya. Sama dengan sebelumnya. Ya. Nah, yang berikutnya ada di ujung sini, ya. Itu operasi modulo tadi, ya. Dan berikutnya sampai ke sini. Tadinya ini adalah di ujung, ya kan menurun tadi. Sekarang ini ada di sini, ini tetap. Nah, di M sama dengan di N1 kita lihat. Ini geser kanan semua, ya kan? Ini kan udah dicerminkan. Geser kanan semua. Nah, yang di ujung ini balik di posisi 0. Itulah operasi modulo. Jadi yang ini pindah ke sini, geser semua satu ke kanan, ya. Nah, yang di ujung sini operasi modulo itu, ya, dia kembali ke awal. Di ujungnya kembali ke awal. Ya, itulah operasi modulo. Yang di N-1 dia balik ke sini. Kalau ini digeser lagi untuk 2 misalnya, ya. Jika 2 kurang M, maka ini geser lagi ke kanan, geser semua satu-satu. Yang ujung ini balik ke awal. Ya. Dan seterusnya kemudian dikalikan dengan delta tadi X1N, ya. X1N, sehingga kita dapat hasilnya kurang lebih seperti ini, ya. Jadi setelah dikalikan dengan X1N, ya. Nah, itulah operasi modulo. Contoh berikutnya X1N sama X2N. Ya, ini sama. X1N sama, X2N sama. Ya. X1K sama dengan X2K, penjumlahan dari WNKN, ya, sama dengan N pada K0, maka X3N, nah ini menggunakan konsep perkalian, ya. Jika ini X1N sama dengan X2N, X1K-nya adalah N untuk K sama dengan 0. Dan 0 untuk N lainnya. Nah, X3K adalah perkalian X1K kali X2K, jadi N kuadrat. Ya. Dia langsung menggunakan samaan, ya, X1K kali X2K. Ini sama X1N, X2N sama dengan 1 untuk N. Jadi L-1, jadi deretannya, tapi ada tambahan 0, ya, tambahan 0 menuju ke periode N. Ya. Nah, tambahan 0, jadi didapat X1K, dapat X2K, kemudian X1K kali X2K bentuknya segitiga seperti ini. Sifat-sifat konvolusi sirkular, ya, dia bersifat konvolusi sirkular di domain waktu, perkalian di domain frekuensi. Ya. Modulasi perkalian di domain waktu, konvolusi sirkular di domain frekuensi. Hah? Kapannya? Setting 2 hari lagi. Nanti. Ya, jadi kalau kita lihat sifat-sifatnya, XN, XK, ya. X1N konvolusi sirkular dengan X2N, ya, rangkuman dari X1K perkalian di domain frekuensi K, bersifat linear AX1N tambah BX2N, AX1K tambah BX2K. Ya. Dualitas XN, N kali minus K modulo N. Pergeseran N kurang M modulo N, itu WN KM XK. Ya. Operasi konvolusi sirkular, ya, perkalian di domain frekuensi. Conjugate, ya, X conjugate minus K modulo N. Sifat simetri XK, ya, X conjugate minus K modulo N. Bagian real XK, ya, bagian real dari X minus KN. Tapi bagian imajiner dari SK minus JMX minus K modulo N. Pasanya fungsi genap, ya. Amplitudonya fungsi genap, fasanya fungsi ganjil. Ya. Konvolusi linier, dua deretan panjang terbatas. Ya. Jika X1N deretannya L, X2N deretannya P, ya. Agar X3N adalah konvolusi linear X1M, X2N, nilainya sama, atau konvolusi linear ini bisa didapat dari konvolusi sirkular. X3N ini bisa dihitung dengan konvolusi sirkular jika diambil periodanya adalah periode N, N-nya L ditambah P kurang 1, maka konvolusi linear ini bisa dikomputasi melalui konvolusi sirkular, ya, melalui komputasi sirkular. Bagian real, misalnya bagian imajiner. Kita masuk ke konsep zero padding. Zero padding, memperpanjang deretan. Ya. Jika diketahui suatu deretan terbatas XN yang panjangnya 4, besarannya 1, berada dari 0 sampai 3, ya, 0 sampai 3, maka jika menggunakan transformasi Fourier waktu diskrit, FWD, kita dapat X E pangkat J omega, ya, dia akan memiliki kurva, ya, sin X per X, tapi ini amplitudenya, tapi fungsinya continue, ya, continue dari 0 sampai 2pi, ya, dia periodik 0 sampai di 2pi. Oke. Jika jumlah deretannya diambil jumlah periodanya, maka frekuensinya, ya, dicuplik setiap 2pi per 4 atau pi per 2, maka amplitudo di pi per 2, setiap pi per 2 dia 0, ya, hasil cuplikannya yang ada di ujung, ya, yang adanya di ujung, yang besarannya 4, ya, ini besarannya 4, ya. Jadi kalau dicuplik 2pi per 4 atau pi per 2, dia 0. Jika deretannya ditambah 4.0 atau periodanya n-nya menjadi 8 titik, ya, artinya dia akan frekuensi pencuplikan fundamentalnya 2 pi per 8, pi per 4, ya. Di antara pi per 2 diambil pi per 4, ya. Berarti ada dicuplik frekuensinya tadi yang kontinunya, berarti ada satu titik, ya, di antara titik 0 tadi ada dicuplik dia, ya. Sehingga gambarnya amplitudonya demikian. Ya, di antara 0 tadi itu ada nilai baru. Kalau dia 16 titik DFT-nya, ini sama dengan mencuplik lagi di antara dua. Kalau dia besar, ya dia akan mendekati fungsi kontinu-nya. Artinya sebaliknya, untuk mendapatkan kontinu, maka n-nya diambil dengan n besar, ya, n besar, sehingga ini menjadi interpolasi, ya. Fungsi kontinu yang di atas ini bisa didapat dari interpolasi dari spektrum diskritnya, ya. Nah, konsekuensinya apa? Wn minus Kn tadi adalah dikomputasinya, ya. Komputasi dari Xn menuju Xk, ya, dari discrete Fourier transform, jumlah komputasi frekuensi, jumlah komputasi perkalian kompleksnya itu sejumlah n kuadrat, ya, dari perkaliannya aja. Komputasi perkalian kompleks n kuadrat, ya. Penjumlahannya n dikali n kurang 1 atau n kuadrat kurang 1. Artinya ada komputasinya setara dengan n pangkat 2. Ya, n pangkat 2. Sehingga jika n-nya diperbesar, maka komputasinya akan kompleksnya n kuadrat. Nah, muncullah algoritma komputasi untuk menghitung ini, ya. Jadi artinya sekarang kalau kita punya deretan terbatas, kita mendapatkan spektrum, ya toolsnya adalah discrete Fourier transform. Tapi ada faktor komputasi yang cukup besar, maka algoritma fast Fourier transform akan berguna untuk mengurangi dari komputasi pak kuadrat menjadi logaritmik, ya, sehingga n logaritmik, jadi menjadi linear, ya, jumlahnya. Nah, disitulah peranan dari fast Fourier transform, ya, untuk mengurangi jumlah komputasi dari discrete Fourier transform.
One of the many uses for the discrete Fourier transform is to compute the spectrum of signals that have been sampled. So we're going to learn how to use the DFT to find the spectrum of discrete time signals, which we've denoted as x of f hat, also to find the spectrum of continuous time signals, x of f. And this involves scaling the frequency axis as well as scaling the DFT coefficients. So recall that the DFT represents a time signal x of n as a weighted sum of complex sinusoids whose frequencies are harmonic or integer multiples of 1 over n. The weights are the DFT coefficients xk, so we're going to derive a spectrum from xk, and of course sampling will be involved if we use a continuous time signal, so we also have to factor in the impact of the sampling interval t sub s. Now there's a couple key facts for finding the relationship between the index of the DFT coefficient and the frequency in the spectrum. First of all, is to observe that x of k is associated with a complex sinusoid whose frequency is k over n cycles per sample. So xk occurs at a digital frequency f hat k of k over n. And continuous time frequency f is f hat times 1 over t sub s, where t sub s is a sampling interval, and that's measured in units of hertz. So the coefficient x of k has associated with continuous time frequency fk, which is f hat k times 1 over t sub s, or 1 over t sub s is equal to the sampling frequency f sub s. So combining these two terms, we have that xk is located at frequency k divided by nt sub s hertz. Now another fact that we're going to make use of is that the DFT coefficients x of -1 is equal to x of n minus 1, and similarly at -2 is the same as n minus 2. So I've drawn this picture here that shows these coefficients map to these negative indices for k. Now the picture I've drawn assumes that n is odd. As we conventionally draw the spectrum in terms of negative and positive frequencies, and the negative frequency information is embedded in the upper half of the DFT coefficients. So in this graphic, we're showing the various axes and their corresponding labels. So I have k, the DFT index, and that's going to go from 0, 1, 2, up through n minus 1. Then in terms of digital frequency or discrete time frequency, f hat in cycles per sample, we normalize k by capital N. So I'm going to have 0, 1 over n, 2 over n, and so on, up to n minus 1 over n. And then to convert that to hertz, we can divide by t sub s, or equivalently multiply by f sub s. So in terms of hertz, our DFT coefficients are located at 0, 1 over n t sub s, 2 over n t sub s, all the way up to n minus 1 over n t sub s. And because the upper half of the DFT coefficients corresponds to the negative frequency DFT coefficients, we can map those down here, and we have, in terms of discrete time frequency, -1 over n, -2 over n, and so on. And in terms of continuous time frequency in hertz, we have -1 over n times t sub s, -2 over n times t sub s, and so on. So the spacing between each DFT coefficient is 1 over n cycles per sample, or 1 over n t sub s hertz. Now 1 over n t sub s is the same as f sub s divided by n. Now the case that I've shown here is for n odd. If n is even, and we use MATLAB's convention, which is to map the coefficient at n over 2 over to minus n over 2, then we have the diagram shown below. The DFT coefficients are spaced by 1 over n cycles per sample, or f sub s over n hertz, and in this case, since n is even, the DFT coefficient at n over 2 maps to a discrete time frequency of 1/2 cycle per sample, and that maps to f sub s over 2 hertz. And again, we're taking this upper half of the DFT coefficients, and we're using those to get the DFT coefficients at negative frequencies. Now there's also the necessity for converting the amplitude. We can see that by taking a signal which is just a complex sinusoid at frequency L over n and has amplitude A, and the spectrum of this signal would have a coefficient A at frequency L over n. If I expand x of n in terms of the DFT, we're going to write it as a weighted sum of complex sinusoids whose frequencies are k over n. So the way that this sum down here is equal to x of n is by setting all the xk equal to 0 except when k is equal to L. And that reveals that A has to be equal to 1 over n x of L. So if I have the DFT coefficients x sub L, I'm going to divide by n to get the amplitude of the discrete time signal spectrum. We have to scale the DFT coefficients by n, the number of samples. It's a consequence of the way the DFT is defined with having this 1 over n factor. So we're going to illustrate this now with an example. I'm choosing a continuous time signal x of t being equal to 2 cosine of 20 pi t plus pi over 4. We're going to use a sampling interval of 1 over 50 and collect 50 samples, so that's a total of 1 second. In that case, x of n is 2 cosine of 2 pi 10 over 50 n plus pi over 4. And I can write that as a sum of two complex sinusoids whose frequencies are 10 over 50 and minus 10 over 50. So in this form, we can read off the discrete time signal spectrum. It should have a magnitude of 1, at minus 10 over 50 and a magnitude of 1 at 10 over 50. So here is the magnitude of our DFT coefficients. I see that I have a coefficient of amplitude 50 at k equals 10 and another one at k equals 40. So the coefficient k equals 10 corresponds to this frequency of 10 over 50. I've taken and am showing the DFT coefficients after scaling the amplitude by n, so I'm going to divide by 50, and that gives me a value for the spectrum of 1, and then I'm going to find my discrete time frequency in cycles per sample. F hat is going to be k divided by n, so this large component at 10 is going to correspond to a discrete time frequency of 0.2, which is identical to 10 over 50. So now we'll take the upper half of the DFT coefficients and move those to negative frequency and display the spectrum from minus 0.5 cycles per sample to 0.5 cycles per sample. And you can see that what happened was this large component that was at 0.8 now is mapped to negative 0.2 cycles per sample, which corresponds exactly to this complex sinusoid with frequency negative 10 over 50. Now finally, we can map this to continuous time frequency, and so now I'm showing the magnitude of the spectrum x of f, and we've obtained the frequency axis by taking discrete time frequency f hat, dividing by t sub s, or equivalently multiplying by f sub s, and we see that what was at 0.2, when I multiply by 50, or divide by 1 over 50, that goes to 10 hertz, and then I have another one at minus 10 hertz, which agrees exactly with our intuition from the cosine, which has a frequency of 10 hertz. You'll notice that the amplitude of the cosine was 2, so the spectrum of the cosine, if we did a Fourier series, we would expect to see a coefficient of 1 in magnitude at 10 hertz and at minus 10 hertz, and that is exactly what we obtained by taking the DFT coefficient, scaling the axis appropriately, and normalizing the amplitude of the DFT coefficient by n. So we'll consider another example which is very similar to the previous one, except instead of having a frequency of 20 pi times t, we now have a frequency of 21 pi t, or 10.5 hertz. And we'll again use n equals 50 and t sub s equal 1 over 50. And one thing that you notice is that 10.5, the frequency of this sinusoid, is no longer an integer multiple of 1 over n t sub s. So the DFT is trying to express this sinusoid using a sum of complex sinusoids, but the available frequencies don't correspond to the frequency of the sinusoid itself. So instead of having just two non-zero coefficients, we're going to expect to see a lot of non-zero coefficients. So here's the magnitude of the DFT coefficients, and then we've scaled these by 50 in amplitude and mapped the axis to continuous time frequency, as well as taken the upper half of the DFT coefficients and shifting them down to negative frequency to obtain the spectrum. And you'll note that the large amplitudes of the spectrum occur at frequencies 10 and 11 hertz, which are on each side of 10.5 hertz, the actual frequency of the cosine. Here's another example where we have a sum of two sinusoids. The first one is a cosine with frequency 10 hertz, and then the second one is a sine whose frequency is 25.9 hertz. Now you'll also note that the amplitude of the sine is 4 times as large as the amplitude of the cosine. We are going to choose n equals 200 and t sub s equal 1 over 100. So this means that the sinusoids being used by the DFT are integer multiples of 1/2 hertz. So the 10 hertz sinusoid should show up at a DFT index corresponding to 20, because 20 times 1/2 gives me 10 hertz, while the 25.9 hertz sinusoid is not an integer multiple of 1/2, so we're going to expect to see a lot of terms associated with approximating this one. The peak amplitude should correspond to a DFT index near k equals 52, because that would represent 26 hertz. Indeed, we have a coefficient when k is equal to 20. That is a single coefficient, and that corresponds to this cosine. And then the sine, which we can't express using a single component of the DFT, requires a large number of non-zero coefficients. The amplitude is roughly 4 times. So now we've taken the upper half of the DFT coefficients from 100 to 199, and we're mapping those to negative frequencies. We've scaled the axis, and we've divided the DFT coefficient amplitudes by n, which is 200, to obtain our DFT version of the spectrum. And you can see that we have a component at 10 hertz and minus 10 hertz, and the amplitude of that component is slightly bigger than 1/2. Now, it should be exactly 1/2 if it was this cosine alone, but we have this other sine who's using all of the DFT coefficients in general, and so that biases the amplitude a little bit. And the sine term shows up at close to 26 hertz. This peak value has a frequency or an x value of 26 hertz, and the amplitude is about 1.9, roughly 4 times the amplitude of the cosine term.